Let's go over a set-associative cache example. Here we have a two-way set-associative cache, 6-bit addresses, one-word blocks, and forward cache. Write-through policy. To calculate the TIO breakdown, it's always very easy to start with the offset because it only depends on the block size. So the block size is 1 word, 4 bytes. We only need 2 bits for the offset build. Then we need to calculate how many sets there are. We went over the formula before, but to calculate how many sets, we first calculate how many slots there are. So the cache size is 4 words, and the block size is 1 word. We have 4 slots in total. Because it's two-way set associated, 2 slots belong to 1 set. So we need to divide 2. So 4 slots divided by 2 slots per set give us 2 sets. This means we only need 1 bit for index. The rest 3 bits is for tag. This is how our cache looks like. We have 2 sets. Index 0 mapped to the first set, index 1 mapped to the second set. For each set, we will have 2 slots. Also RRU bits. For each slot, we will have a valid bit, tag bits, and then data block. Offset is just index to the data block. From here, we can see that we need 37 bits per slot, and 37 times 2 equals 74 bits per set. In total, we need 148 bits to implement. Recall that we need 150 to implement the fully associative, and 140 for direct mapped. So for set associative, it's expected that you will have a number somewhere in between. Alright, here's my favorite part. We're going to show how main memory blocks are mapped to cache slots. Here, each block in main memory can only map to 1 set, but it can map to 2 slots. So for the first block of memory, we can see that the index is 0, right? So index 0 means it only can map to set 0, but because we have 2 slots in set 0, it can either be mapped to the first one or the second one. We can see how blocks are mapped to the cache by colors. When the cache receives a memory request, let's see 001011, look at the index field first. It's 0, so it maps to the first set. And then for each slot in the set, we need to check the valid bit first. If it's valid, we compare the tag bits. If the tag bits matches, it means it's a cache hit. The block is already contained in the cache. If it doesn't match, we still need to go back to memory and bring the data block in. Alright, here's the sequence of memory address X's. It's the same sequence for fully associative cache. Let's see what's the difference here. In the beginning, we have a cold cache. So valid bits are all 0. Memory address 0 will have a miss. Because the index bit is 0, we look at the first set, change the valid bit to 1, record the tag, and bring the data block in. The second address is 2. The index bit is 0 again for the first set. The valid bit is 1, then we compare the tag. It matches, so we have a cache hit. Then we have address 4. The index bit is 1, so we're moving on to the next set. The valid bits are all 0. We have a cold cache, so we put the data into the first slot. Change valid bit to 1, record the tag. Next one is 8. Index bit is 0. We're going to look at the first set. Valid bit is 1. We compare the tag. It doesn't match. So we can place the data into the second slot of set 0. Change the valid bit to 1, record the tag, and bring the data in. So far, we have 3 misses and 1 hit. Alright, moving on, we have 20. Index bit is 1. We compare the tag bits with the first slot. Doesn't match. So we put the data saved at address 20 to the second slot. The next one is 16. The index bit is 0. Compare the tag with first slot. 010 doesn't match 000. Compare the tag with second slot. It also doesn't match. So we need to evict 1. Because 001 is the most recently used one, so we need to evict 000, the first slot. So we're going to change this 000 into 010 and change the data. Next memory address is 0, index 0, so it means first set. And very unfortunately, we just evict the block contains the data from address 0, so we need to evict the second slot because that's least recently used. From here, we change 001 to 000 and change the data. Alright, so the last one is 2. Index is 0, and then we compare the tag bits, it matches with the second slot, it's a cache hit. We have 6 misses for 8 requests. It's the same with direct mapped cache, but you can tell that how we're saving the blocks into cache is very different. And all slots in the cache are used. We're not wasting space here. We all know that the worst case for direct mapped is the ping-pong effect, with a repeating pattern of 2 memory access into the same cache slot. It makes hit rate equal 0. For Set-Associative, it's still possible that we're going to hit that case, with a repeating pattern of at least n+1 addresses that maps the same set. Let's look at this specific example. A repeating pattern of 3 addresses maps into the same set. Okay, so first address is 0. We place the data block into the first slot in the first set. The second one is 8. Same index, different tag, so we place the data block into the second slot in the same set. Okay, then we have 16. Same index, different tag, so we will need to evict one block. Because the first one is least recently used, we're going to evict that one and then put the new data in. And that comes to worst case. We're accessing 0 again. But the block that contains the data from address 0 is just evicted. But since we're following the least recently used policy, we have no way but evict the second slot, which stored the data at address 8. But the next address that we want is 8. It's a very sad pattern because we keep evicting the data block that we need right before we request the address. The hit rate is 0 now. Lastly, let's work through a TIO breakdown question. Okay, we have a 32-bit address space, 32 key B, 4-way Set-Associative cache, and 8 word blocks. Again, for this kind of question, it's easier to start off calculating the bits for offset because we have 8 word blocks, so we need 5 bits for the offset. And then we need to calculate the index. 2 steps. First, calculate the number of slots, which equal the cache size divided by the block size. Cache size is 32 KB, 2 to the 15 bytes. Block size is 8 word, 32 bytes. So we will have 2 to the 15 divided by 2 to the 5. So we have 2 to the 10 slots in total. And then because it's 4-way Set-Associative, 4 slots are in the same set, we need to divide by 4. That gives us 2 to the 8 sets. So we need 8 bits for the index field. And the remaining bits are for the tag. B is the correct answer. To summarize, we talked about fully associative cache, where the block can go anywhere, a direct mapped cache, where the block can only go into one specific location in the cache, and end with Set-Associative cache, which is a compromise of fully associative and direct mapped. So the cache is split into sets, and each set will have n slots to place memory blocks. Because for n with Set-Associative cache, we only need to look up for one set at each time, so it saves lookup time. And because we have multiple slots available in one set, it makes it difficult to fall into the ping-pong effect that direct mapped cache suffers. However, it's still possible to get a bad performance as we've seen in the previous slides. Therefore, the conclusion here is that no cache is perfect. The ability that we want you guys to have after learning about cache is that when you're giving a program, by looking at the code, you can tell which type of cache can produce the best performance. Or other way around, when you know the design of the cache for the system you're working on, you can find a way to write your code so it can maximize performance.